Okay, random variable is a function that assigns a real number to each outcome of an experiment. For example, a National Health and Nutrition study asked the respondents about their daily hours of TV or video use. The answer to that question, which we label X, is a number from 0 through 6 according to the number of hours of use. X is a random variable, and P of X is the probability of each value of X. So this table is going to give the possible outcome of the previously mentioned study along with the probability of each outcome. So X is our random variable, and it is representing the number of hours of TV or video use. And the results of the study came up with hours from 0 to 6. So X is assigned the values 0, 1, 2, 3, 4, 5, and 6. P of X is the probability of X. It's the probability that a randomly chosen person from the study will have that designated number of hours of television or video usage. We could also write the same information as a set of ordered pairs, and you see that listed here. And often we also display this graphically on a type of a bar graph called a histogram. And this is what a histogram will look like. Note that the values of X are on the horizontal axis, or the x-axis. The values for P of X are on the vertical axis. This type of display tells us more about the relative size of each probability and how the probabilities are distributed than a table or list does. And we'll get into it a little bit further, but you can tell some things about the shape of the distribution and all that from looking at a graph. When we do statistics, we like to be very visual with it. We like to have visual displays. Okay, a couple of examples. A, give the probability distribution for the number of heads showing when 2 coins are tossed. And B, draw a histogram for the distribution in the table that you're going to do in part A. Find the probability that at least 1 coin comes up heads. All right, pause the recording, see if you can do this, and resume to check your answer. So we're going to let X be the random variable number of heads. That's what X is going to represent. And when we think about it, there's 3 possibilities. If you toss 2 coins, you could have no heads, you could have 1 head, or you could have 2 heads. Now, we need to list the different ways this can happen. So when we flip 2 coins, we could have tails, tails, that would be nose heads, and there's only one way that happens, and that's when both coins are tails. We could have heads, tails, or tails, heads. And in both of those cases, we have 1 head, and there's 2 ways that can happen. And then finally, we could have both of them heads, and there's only 1 way. So our X is 0, 1, and 2. The probability of 0 is 1/4. The probability of 1 is 1/2, or 2 out of 4. And the probability of getting 2 is 1/4. Okay, and for B, there's our probability distribution. Now the cool thing is that our TI graphing calculators can create histograms for us. What you're going to do is you're going to push Stat and then Edit. And you're going to have the list come up. You're going to enter the X values in list 1 and the values for P of X in list 2. When you're done with that, go to Stat Plot, select Plot 1, and set it up as indicated below. Okay, there's our list, and there's how you want to set it up. Notice we've turned it on, and notice under Type, we've gone all the way to the end of the top row and selected what looks like a bar graph. We also have XList as list 1 and frequency as list 2. Those are important. And when you're done with that, you're going to go to Y1 and Y equals, and clear out any equations you may have. And then you're going to set up an appropriate window. Now you can use Zoom Stat, which will give you a good starting place, but usually with this kind of a bar graph, you want to adjust it from there. You might want to make your scale a little different. The scale is going to determine how wide each bar is, and there you go. So there's our bar graph done on our calculator. The expected value is the value you would expect to see on average. To find the expected value, we multiply each x by its probability, and then we add all of these products together. And that's what this is saying. So you take each x value, you multiply it by its own probability, and then all of these products you get for the entire set or the entire table, you're going to add together. Okay, here's an example, and this is the example with the TV and video usage, and I put the chart here so you don't have to flip back. Find the expected number of hours per day of viewing. Now I'll give you a head start on this. You're going to do 0 times 0.13, 1 times 0.24, 2 times 0.33, keep going all the way down the chart like that, and then add all of those products together. Pause the recording, see if you can finish this problem, and then resume to check your answer. Okay, you see here where it's all spelled out for you, how we multiplied, we added them together and got 2.07. What that means is that on the average, a respondent of the survey will indicate 2.07 hours of TV or video usage. Here's an example from business. You've got a symphony, they want to raise money. They're going to raffle off a microwave oven worth $400, a dinner for 2 worth $80, 2 books worth $20 each. They're selling 2,000 tickets, and they're $1 each. We want to find the expected value of winning for a person who buys 1 ticket in the raffle. Now, let's try this, but what you need to realize first as you go to set this up is that we want the expected value of winning. So what you need to take into account is the $1 they're spending on the ticket. So if they win the microwave oven, it's going to be $400 minus 1, or $399 value that they win. The dinner for 2, they'll only actually net $79. Each book will be $19. Those who win nothing, their loss is going to be represented by a minus 1. Okay, the probability, there's 2,000 tickets. Okay, so your probability of winning a microwave oven is 1 over 2,000. All right, with that information, see if you can set up a chart like we did before, and then do the multiplication and find the expected value for winning for a person who buys 1 ticket. Pause the recording, give this a try, and resume to check your answer. Okay, this is what we just said about how you have to actually find the net winning. Okay, here's our chart. Your chance of winning the microwave is 1 over 2,000. Of winning the dinner for 2 is 1 over 2,000. The 2 book, there's 2 books, so that's 2 over 2,000. And then all the rest of the people are going to lose $1. So that's 1,996 out of 2,000. So you're going to multiply the dollar values by their probabilities and then add them together. When we do that, we get a negative number, which is actually fine. That can happen with expected value. What that means is that on average, a person buying a raffle ticket will actually lose 74 cents. Now, it's not possible to lose 74 cents in the raffle. Obviously, you lose $1 or you win a prize, minus the $1 you pay. But if you bought tickets in many such raffles over a long period of time, you would end up losing 74 cents per ticket on average. And that's exactly what the expected value means. It doesn't necessarily mean it's going to happen in 1 or 2 tries, but as with all probability and statistics, this is something that happens in the long run. Let's try another one. Each day, Lynette and Tanisha toss a coin to see who buys coffee at $1.75 a cup. One tosses, the other calls the outcome. If the person who calls the outcome is correct, the other buys the coffee. Otherwise, the caller pays. Find Lynette's expected winnings. All right, pause the recording, see if you can figure this out, and then resume to check your answer. Okay, assuming they're tossing an honest coin, that Tanisha tosses the coin and Lynette calls. The possible results and the probabilities are this. So if the result is heads and she calls heads, she wins. If it's heads and she calls tails, she loses. If it's tails and calls heads, she loses. If it's tails and she calls tails, she wins. So there's 4 possible outcomes, and each has a 1/4 possibility of occurring. So she wins $1.75 whenever the results and the calls match. She loses $1.75 when there's no match. So her expected winnings, well, basically she is expected to break even in the long run, which is kind of makes sense if you think about it, because your chance of calling a tossed coin correctly is 1 out of 2. So you would expect her to win half the time and lose half the time over the long run. Okay, a fair game is a game where you have an expected value of 0. In other words, a game where you break even. Now you got to keep in mind that casinos do not offer fair games. And you know, part of the reason for that is they're a business. They have to pay the bills, they have to pay their employees, and if they are breaking even, that's not going to happen. Casino games have expected winnings for the house that vary from 1.5 cents per dollar to 6 cents per dollar. All right, so we're going to look at an example involving the roulette wheel. We've looked at the roulette wheel before as far as probability goes. So read over this question, pause the recording and try it, and then resume to check your answer. Okay, for this bet, there's only 2 possible outcomes. Either you win or you lose. The random variable has an outcome of +1 if the marble lands in the red slot, and -1 if it doesn't, because you're betting $1. So you either gain $1 or you lose $1. So we want to find the probability for the 2 outcomes. There are 38 total slots, 18 are red. The probability of winning $1 is 18 out of 38. You'll lose if you hit anything else, and there's 20 that are not red. So 20 out of 38, you're going to lose. So here's our little probability distribution table. We multiply everything out. We see that in the long run, you're going to lose 5 cents, 5.3 cents on every dollar bet on red. And you know, keep in mind that that's one of your safer bets because there are so many red slots. So in the long run, you're going to be losing. Here's another example. Suppose that age 50 you receive a letter from Mutual of Mauritania Insurance Company. According to the letter, you must tell the company immediately which of the following 2 options you will choose. You could take $50,000 at age 60 if you are alive. Of course, you don't get anything if you're not alive at 60. Or take $65,000 at age 70 if you're still alive to collect it. Based only on the idea of expected value, which do you think you should choose? Pause the recording, think about it for a minute, see if you can come up with an answer, and then resume to see how you did. Well, life insurance companies have these tables that show the probability of a person living a given number of years into the future. In fact, there are people that that's their whole job, is to figure out stuff like this for insurance companies, to figure out liabilities. And if you enjoy statistics and probabilities, that might be something you're interested in. That job is called an actuary, and there's not a whole lot of them around, and they get paid pretty decently. So if this is something that interests you, it might be something you want to look into. Anyway, from a recent such table, the probability of living from age 50 to 60 is 0.88, while the probability of living from age 50 to 70 is 0.64. Now, of course, it wasn't very fair to give you the question without giving that information first. But anyway, let's see what we have here. The first option is 50,000 times 0.88 plus 0 times 0.12. That's $0 if on the 12% chance you die. And then the second option is 65,000 times 0.64 plus 0 times 0.36. And we see that you actually have a better chance if you collect on the first option and you go ahead and take the $50,000 at age 60. This is extra practice, so try these problems. Pause the recording while you do that, resume to check your answer, and continue in that manner till the end of the video.